Dear students, the topic for today's lecture is deadlock characterization. Okay, in the deadlock characterization, we will try to understand the four conditions. And when these four conditions hold simultaneously, then may or may not the deadlock will occur. Okay? Remember, when these following four conditions hold simultaneously, then we can say deadlock may or may not occur. Okay? It doesn't mean that when these four conditions hold simultaneously, then the deadlock will occur. No, may or may not. Okay? The possibility of deadlock will rise. Okay, guys, let's have a discussion about the first condition, which is mutual exclusion. Mutual exclusion means one or more than one resources are not shareable. Only one process can use it at a time. It means, dear students, let's suppose, you know that our system consists of multiple resources. If you remember the previous lecture, let's suppose I have a single instant resource. Let's suppose this is a single instance resource, okay? And the single instant resource, you know, it consists of one instance. Let's suppose this is R1. R1 is consist of W1, where this is represent what? Instance. You know what does it mean, okay? So our system is consist of R1, and where R1 is consist of one single instance, and you know that single instance resource is not shareable. But I have two processes, P1 and P2. Okay. P1 is arrived where P2 is also arrived. If at the same time P1 request for this resource and P2 also request for this resource, you know that these two processes will compete each other to have this resource, and such thing will create deadlock. Maybe the P1 will able to hold this resource and the P2 will not able to hold the resource, and they have to wait. So just because of requesting at the same time for the same single instant resource, one process will go to a particular situation. It means a waiting situation, and that can be a reason of deadlock. That's why the system must decide that it's a single instant resource, and this single instant resource is not shareable. This resource is not shareable. You know, shareable means what? Whenever the availability of a particular object is possible for more than one requester. Like here I have two requesters, and this is a single instant resource. The system must decide that it's not shareable. Why? Because the system cannot allocate this one single instant to two processes. So one process should request, another process should request late, okay, or should not request, because this request will create a problem. If the P2 will not request, then the P2 will not be in the waiting state, okay? So dear students, whenever two processes are going to make a request for this non-shareable or single instance resource, then this is called mutual exclusion. And this mutual exclusion will cause deadlock for any of the process. We cannot show that for P1 or for P2, but the possibility of deadlock is for any of them, okay? So this was mutual exclusion, and mutual exclusion can be the reason of deadlock. As I told you before, that may or may not the deadlock will occur when these four conditions comes true. So dear students, one conditions come true and the possibility of deadlock is erased. The second condition is, okay, the first condition is finished. The second condition is hold and wait. Hold and wait. And let's try to understand hold and wait situation mean what. Okay, so this was condition 1. Let me write here. Condition 1, and that was mutual exclusion. Any question here? Okay, no question.
No question, sir. Thanks.
Very good. So it's a request, and it's also a request. And remember, when this P1 and P2 are requesting, it means at this time it is T1. It is time 1. Okay, that's why the problem will rise. Good. Let's continue. I'm going to save this for you guys and we clean this. The second condition was what? Hold and wait. Hold and wait. Now, let's suppose, okay, let me write the second condition. Condition number 2. And this condition is hold and wait. Okay, guys. I have 2 resources. For example, R1 and R2. Both resources are, let's suppose, single instance resource. Single instance resource. So R1 and R2. I have a process. This process is P1. Okay, so now the P1 is holding R1. The P1 is holding R1. You know that this arrow is holding arrow. Do you remember in the previous lecture we had discussion that whenever a P1 is requesting the resource, so this arrow will be used. And whenever the resource is assigned, then this arrow will be used, okay? Okay, guys. So the resource R1 is holding by P1, but where P1 is saying that R1 is not sufficient for me. So that's why the the P1 will make a request to use R2 also. And where R2, let's suppose, R2 is already utilized by P5, for example. There's another process, P5. So the P5 is using R2. Okay. So this is the case. And now let's understand in this case, what is hold and wait. See, dear students, focus on the P1. P1 is holding R1. P1 is holding R1. Okay. Holding R1. Where P1 is waiting for R2. So P1 is waiting for R2. So this is called what? Hold and wait. So this hold and wait situation will create deadlock for this P2. So it means that we can say possibility of deadlock for P1. Possibility of deadlock for P1. That's why we can say may or may not, okay? Possibility of deadlock. Habib is saying that why possibility? Why the deadlock is not confirmed? See, what will happen if the P5 release the R2? Then there is no chance of possibility deadlock. But if the P5 will not release the R2, then the P1 will be in the deadlock situation, okay? That's why we will say possibility, it's not confirmed. Is it clear, dear students? Hold and wait.
Yes, sir. Thanks a lot.
Good. Let's continue. So this was the second condition. If this condition take place, or if this condition hold, so then the possibility of deadlock is here, okay? The condition number 3 is no preemption. The condition number 3 is no preemption. You know, we already had discussion about preemption and non-preemption. Preemption is a feature of operating system when operating system can take back resources from a particular process when a high priority process is arrived. And non-preemption means when the operating system cannot interference, and when the operating system cannot take back the resources from a running process. So dear students, the no preemption mean when a process, okay, no preemption, this is the third condition. A resource cannot be taken from a process unless the process release the resource. So it means when the such type of situation will be there, if your operating system will not able to take back the resources from the process, and there the operating system and the processes will wait that when the process will release the resources. So such type of condition can also create what? Deadlock situation. Let me explain this. Okay, now I will use the same diagram for the condition 3, okay? Condition 3, which is what? No preemption, okay? No preemption. Okay, guys, you can see in this diagram that P1 is waiting for R2. P1 is waiting for R2, but where R2 is holding by P5. Let's suppose P5 is not that much important process. P1 is very much important process where we cannot tolerate a waiting situation for the P1, but we can tolerate a waiting situation for P5. In current diagram, the P5 is not going to release the R2, but where P1 is waiting. So until such situation will remain, then the P1 will be in a deadlock situation. So we are saying what? The operating system should interrupt. The operating system should take back the resources from the P5. But if the operating system, let's suppose I have, this is my OS. OS. And the OS cannot take back the resources from this. Okay? If OS cannot take back the resources from the P5, then what will happen? No preemption. It means that OS cannot take back the resources, okay? Cannot take back the resources. So when it's taken, when it cannot take back the resource, it means that the no operating system have no preemption capability, okay? And the P1 will be in the deadlock situation, okay? The P1 will be in the deadlock situation. Is it clear? It's very easy, but little tricky. See, dear students, I'm repeating this. P5 is holding the R2. P1 is waiting for R2, okay? But where the operating system don't have this capability to take back the resources from the P5 and allocate them to P1. And when it cannot take back the resources from P5 and it cannot allocate them to P1, so this is called no preemption. And no preemption can also create the possibility of deadlock. Okay, guys? So this was condition 3. Remember, you have to understand these 4 characteristics because the solution of deadlock will also behind these same conditions, okay? When we are going to handle the deadlock, we will try to solve the same problems. That's why you have to understand these problems. So no preemption of operating system can also cause deadlock. Same. Let's come back to the slide. The final deadlock characteristics or the final deadlock condition which can make possible the deadlock is circular wait. Remember, dear students, a set of processes are waiting for each other in a circular form. Whenever a circular shape is generated, just because of this hold and wait process, okay? So we will say that possibility of deadlock is there. If you remember, same like loop, circular shape, okay? If whenever the processes are waiting for each other, when they will release the resource, in this waiting and holding situation create a circular shape, then we will say possibility of deadlock is here. And let me explain this how. Okay guys, I will use the same diagram, okay? So it's condition 4. And condition 4 is what? Condition 4 is circular wait, okay? Circular wait. Okay, let's suppose after a particular amount of time, for example, P5 is saying that R2 is not sufficient for me. I am going to make a request to have R1. So now you can see a circular shape is occur here. Why? Because P5 is also in holding and waiting situation, okay? So P5 is holding the R2 and P5 is waiting for R1, okay? So waiting for R1. And just because of this holding and waiting, this situation is created. See? Okay. So this is assigned for this. They are waiting for the R1. R1 is assigned for P5, where P5 is waiting for R1. So a circular shape is occur. So there is a circle. And the bad news is that in this circle, I have single instant resources at this both sides. They are single instant resource. So this will enhance, or this will make more possibility of the deadlock. Whenever in a circular shape we have single instant resources, then the possibility of deadlock will be increased. But when you have multi-instant resources in a circular shape, then the possibility of deadlock will be decreased. Okay, this is another thing. But you have tried to understand that right now a circular shape is occurred just because of holding and waiting situation. And this circular shape will create what? Possibility of deadlock. And this possibility will be increased when we have single instant resources. This possibility will be decreased when we have multi-instant resources. Is it clear, guys? So these were the 4 conditions. When these 4 conditions become true, then the possibility of deadlock is there. Very good. So let's continue. Okay, guys. Now we will try to understand resource allocation graph, because that graph will help us to understand the further topics, okay? Resource allocation graph. This is very much easy graph because you guys are already familiar with this. How? Let me explain this, how you guys are familiar with this. You know, dear students, a set of vertices V and a set of edges E. Our computer consists of this thing. It means that in our computer, such situation will be always there, because that our computer will be consist of some processes, some resources, and those processes will make requests to utilize those resources, and the operating system will allocate those resources. So because of that, a set of vertices V and a set of edges will be there, and we will represent them with the help of a graph. So where we represent processes, okay, and resources. We represent what? Processes and resources. That's why we are saying we is partitioned into two types. P, processes, R, resources. And our system will be consist of multiple processes, and also our system will be consist of multiple resources. So this was the first thing of the resource allocation graph, which was V. Now the second is ages, where we have two types of ages: request age and assignment age. The request age, when the age is directed from process to resource. So this is called what? Request age. Assignment age, when the age is directed from resource to process. So this is what? Assignment age. And let's use them in a diagram or in a graph. So now these are the graphs. As I told you before that we will have vertices and edges, where vertices mean we will partition in two things: processes and resources. The processes will be represented by the circular shape. The processes will be represented by circular shape. That's why in my previous examples, I always represent a process by a circular shape, okay? Because based on the resource allocation graph, I draw those diagrams, okay? And the resources will be represented by this rectangular shape, okay? And when it is a single instant resource, it will be consist of a single box. When it is a multi-instant resource, we have to represent them with a multiple instance or multiple inner boxes, okay? So like this is a single instant resource and this is a multi-instance resource. So the single instant resource also called dedicated resource. Dedicated resource means not shareable. Multi-instant resources are called shareable resources because we can share this resource with multiple processes at one single time. And this is the example of ages. P1 is requesting R1 specific instance. So see, they will use what? Age, request age. The particular instant of R1 is assigned to P1. So here, assignment age, okay? So this was resource allocation graph. And let me draw a resource allocation graph with deadlock or without deadlock, okay? Resource allocation graph without circle. So dear student, this is a resource allocation graph without circle. So I don't have any circle here. How? You have to focus. This is my system. Inside the system, I have two processes, P1 and P2. I have two resources, R1 and R2, okay? So P1 arrived, P1 need this resource, P1 make a request. The resource was free, the resource is assigned, no problem. P2 arrived, P2 need this resource, R2. The P2 request for R2 and the R2 was free, the R2 assigned to P2. So see, no problem occur because every single thing is, everything occurred according to the normal procedure. And if you remember the resource allocation model, which we had discussed in the previous lecture. So everything occur accordingly. That's why no circular weight is here, no hold and weight is here, and no mutual exclusion here. So it means that right now this resource allocation graph is representing a system with no possibility of deadlock. Okay, remember, request, it was free, and that's why it is assigned, okay? It's assigned. Okay, guys, let's continue. Example of resource allocation graph with a circular shape. Okay, so see, dear students, but there will be no deadlock, okay? If there is a cycle, see, if there is a cycle in the resource allocation graph, then deadlock will may or may not occur. When deadlock will may or may not occur. Remember, circular weight doesn't mean 100% confirmed deadlock. If you remember, I told you circular weight, when the circular weight is occur, possibility of deadlock will be there. And this possibility will be increased if the resources are single instance. And this will be decreased if the resources are multi-instance, okay? So focus on this diagram. I have a circular shape here, a closed circle. Why? Because I have R1, R2, okay, P1 and P2. R1 is assigned to P2. P1 is waiting for R1. This R2 is a single instant resource. One instant is assigned to P1 and another instance is assigned to P1. Okay, so one instant is assigned to P1 and one instant is assigned to P2. Dear students, so because of this hold and wait, because the P1 is waiting for R1, the circle is closed. So it doesn't mean that a deadlock, okay? Then the deadlock will not occur. Because why? There are two instances and both instances are assigned to both processes. So it means here both don't wait. Maybe they will not wait for a long time. Maybe very soon the P2 will release R1 and the P1 will use that. So here the circle is open. So it means we are talking about what? Circle. So in this place, the circle is closed. We have circle. And this circle mean may or may not deadlock, okay? Okay, let's try to understand two more circular shape diagrams. Okay, guys. So you can see here, I have two diagrams, 1 and 2. Here I also have a circular shape, and circular. Here, the deadlock possibility is high, and here the deadlock possibility is very low. That's why based on that, I write here, resource allocation graph with the deadlock, resource allocation graph without deadlock. But how? Let's try to understand. You can see here, P1 is requesting for R1. This instant is assigned to P1. Okay, and the P2 is requesting for R3, where P2 already hold the R1 and the second instant of R2, where the P2 is waiting for R3, but R3 is assigned to P3, and P3 is waiting for this instance of R2. So now, what do you think? You know here, the P2 is a very greedy process. Very greedy process. The P2 is trying to find more resources. That's why he make a request for R3. So what do you think? Is P2 will release this resource? This instance? Of course not. What do you think? Is this P2 will release this R1? Of course not. Why? Because P2 is a very greedy process. Greedy process means very needy process. It's required more resources. And unfortunately, the P1 and P2, they are waiting for a process which is already suffering with a lack of resources. So it means that there is very less chance for P2 to release this R1 and the second instance of R2. And this less chance will create more chance of deadlock for this P1 and P3. And we will say that here the deadlock may occur. The deadlock may occur. We can, right now it's a deadlock, okay? Right now it's a deadlock. Why we are using may? Because if the P2 is not shut or killed by the operating system, then they will remain the P1 and P3 in a confirmed deadlock for an unknown time. So in this diagram, we have deadlock. But in the second diagram, there is no deadlock. Why? Because at both sides, the R1 and R2. They are multi-instance. They are multi-instance. In this first diagram, the bad luck was that R1 and R2 both are single instance. They are single instance resources. And these two single instance resource increase the ratio of the possibility of deadlock. And that's why we say here the deadlock is already occurred. Okay, guys, here P1 is waiting for this instance, and where this R2 instance is assigned to P1. Okay. This second instance of R1 is assigned to P2. Very good. And here, this instead of assigned to P4. Who is waiting? Okay, this is assigned to P3. Okay, the waiting edges are 2. Just the waiting edges are 2 edges. P3 is waiting for this instance, and P1 is waiting for this instance. These two yellow lines are waiting lines. So you can see here we have just only 2 processes in a waiting situation, where the P2 and P1 is a very small processes. They don't wait for any other process. So there are more chance then the P2 will release this resource. When the P2 release this resource will be assigned to P1. And when the P4 release this resource, so then this resource will be assigned to P3. That's why here we will say that there is very less ratio of possibility of the deadlock, and based on that we can say the deadlock may not occur. So dear student, this was graphs which representing the resource allocation pattern, and based on this diagram and based on this pattern, we can say that the possibility of deadlock is less or high. High possibility of deadlock mean deadlock, low possibility of deadlock mean may not. Okay. So these are the basic facts. If graph contains no cycle, no deadlock. If there is no cycle or no circular shape, it means no deadlock. There is 0% of deadlock possibility. But if there is a graph, then may or may not. Okay, the possibility of deadlock. As I told you that if one instance per resource type, then deadlock possibility is high. If several instances of resource type, then low possibility of deadlock. And here we will say may occur, and we will say may not occur. Okay, shayad show, shayad na show. Okay. So this was the basic facts.